Hello, welcome to another video of design and analysis of reconfigurable systems. Today we are going to talk about hard processing systems. So on our DE1-SoC board, the configurable part, that is the FPGA, comes along with a ARM processor called as hard processing system. So this is packaged with the Altera chip. So both the configurable part and ARM processor both come pre-packaged in our Altera chip that is mounted on our DE1 SoC board. So today we are gonna program the hard processing system using C code and control few of its peripherals. So the Altera Cyclone 5 chip, as I said, comes along with FPGA and the ARM processor, and it also has few peripherals that we can use, mainly the VGA port, the Ethernet port, two USBs, one serial communication, one SD card reader, some of the LEDs and switches. Here you can see user LED, user button, HPS reset and warm reset buttons. So these are the main peripherals that we are going to look into, which are hardwired to our ARM processor. In this, for this example specifically, we are going to target only the user LED and the user button. So we will I've already designed as a C code which will turn on the LED, read the user button based on the user button status, trigger the LEDs to turn on or turn off. So this is the C code that I'm going to use that is going to control the peripherals. So in this code, the main functionality is to turn on the LED initially, turn it off, and do the cycle for two iterations, and then in an infinite loop, check the button status. If the button is pressed, the LED should be turned on. If the button is not pressed, then the LED will be turned off. Here initially the LED will be turned on for uh, half a second and then turned off for half a second. So it's each iteration is a 1 second iteration where half the time the LED will be on and the other half the LED will be off. So this iteration will happen twice, and then it will enter a infinite loop, uh, scanning the value from the user button. If the button is pressed, immediately the light will be turned on, and since it is a while loop, as long as the button is pressed, the LED will be continuously turned on. As soon as we let go of the button, the LED will immediately turn off. So this is the functionality that I have coded, which I'll be running on the ARM processor. And to control the ARM processor or provide inputs to the ARM processor, since I'm running Linux over image on the DE1-SoC board using the SD card, where I've burned the Linux operating system onto the card and inserted that to the board. So the Linux OS provides us a terminal window for us to provide the inputs or control the ARM processor. So I'm going to communicate to the board using serial communication. As I mentioned, one of the peripheral for the ARM processor is a UART communication bus, which connects which can be connected to our computer, which will be monitoring the serial data. For that, I'm using an application called as PuTTY, which will monitor the serial data. Upon connecting to my device, these are the parameters that I'm gonna give. So I'm gonna look at the serial line COM6. The board runs at a baud rate of 11.5200 with a data bits of 8 and stop bit as 1. So once the board has turned on, we can start reading the serial data. As you can see here, the operating system is booting up. So once the boot up has been done, we get this Thoracic logo, which is one of the indicators that the booting has been successful. So first we will log into our Linux OS. So once that is done, I've already inserted my USB thumb drive where I've stored all the executable files to run my code. So we'll first scan the USB devices that are connected to the board. So this will list out all the USB devices that are connected. Initially, this will be the boot drive. As you can see here, it is pointing out as Linux, and also it will provide details of the other drives. So since in my case, it is just two devices, two drives. One is the boot drive and the other one is the thumb drive or the USB drive. So I'll just provide the command to mount it, and here the name is dev/sda. So I'll just give that command, the instruction to read this port and assign it to one of the directory. I've already created a directory on my device which will be where the USB will be mounted. So I've just named it media USB drive. Yeah. So by running this command, Linux will mount the thumb drive to this folder media/USB drive. So it was a successful mount. Let's change the directory to our respective directory where we have mounted the drive. Let's do an ls to see the content. System value information, HPS GPIO, AES, my first HPS. So these are the three executables that I have. Here I'm only gonna concentrate about HPS GPIO since that is the code that targets the peripherals. To run that, all you have to do is /HPS_GPIO. Let's run the executable. As you can see, the LED turned on twice and it turned off. Now it is waiting for the button to be pressed. So by pressing, I have not pressed it yet, I have just kept it on top of it. So as soon as we press the button, the LED will turn on, and once you let go, the LED will turn off. And as long as you hold the pressed button, LED will continue to be turned on since we are running on an infinite while loop. So this will go indefinitely as long as the button is pressed. As soon as we let go, the LED will turn off. Since it is running in infinite while loop without any exit criteria, we'll have to manually terminate the code. For that, it is Control C. So this will kill the current running process. We can run it again to see the LED being turned on and waiting for the user button. So I'm running the code again. The LED turned on twice, and now it is waiting for the user button to be pressed. As soon as we press it, it will turn on. Let go, it will turn off. So yeah, that was the main functionality that I tried to implement, where I wrote the C code and ran it on the ARM processor that is built along with the FPGA chip on our Altera Cyclone 5 chip. Since we have, I'll also give a brief description how to exit or shut down this FPGA. So once all our processing is done, or any of our functionalities or any of our use case is done, we'll just have to go back to our root directory, cd home root. So from the root folder, once we are in the root folder, only then we get the complete access to either mount the drives, unmount the drives, or shut down the board processor. So we'll just give umount and the directory where it is the drive is being mounted to. Ours is media USB drive. So by running that command, we have successfully unmounted the USB drive. This is basically the eject option that is available on Windows. So once that is done, I'll just give it a shutdown command. So this command will shut down the processor and asks it to kill any processes that are currently being run and shut down in a faithful way so that it will not harm the processor. System is going to shut down, halt now. So it is sending the processor term signal. As you can see here, it is stopping the other processes that are running. It is unmounting any drives that it is currently using. For example, in our case, it is running the boot drive, so it is unmounting that. And as you can see here, the system is halted. That means the processor has shut down. So we can go ahead and turn off the boot. So yeah, that's a simple code that I wrote that which controls the peripherals that are connected to the HPS, the hard processing system. Yeah, that's it, guys. Hope you learned something today. Thank you for tuning in. Have a great day.